Morning, everybody. Today is our fourth day, I guess, and today's the first talk. We have three talks this morning, just like had the other days. First talk is going to be Hayek Hakoban, and he's going to talk about nuclear hadronization studies at JLab, past, present, and future.
So, I use this one.
Whichever one you want.
Thank you for organization of this nice event and conference. I am Hayek. I'm from Universidad Técnica Federico Santa Maria, which is in Valparaiso in Chile. And also I represent the scientific center, Centro Científico Tecnológico de Valparaíso, which is inside the university. So we have a lot of activities. It's a multidisciplinary center focused on technology, but we have, I think this one also is working.
No. Take that. Yeah, then some money.
So we want to use this.
Yeah, so put close here for the people in the.
Now it's fine. Yes. So I represent the Santa Maria in Valparaiso, Chile, also a scientific center, which is a multidisciplinary center, mostly focused on technology, but we have a big part dedicated to particle physics. It's theoretical and experimental particle physics. We have participation in CERN, in Jefferson Lab and Fermi Lab, and also we build some detectors for GlueX, for instance, and also for Atlas upgrade. I will talk about a specific experiment in Jefferson Lab. Our group is very involved. It's hadronization studies in the nuclear medium, and this idea to use nuclear as a laboratory to study hadronization and also everything which is related to that, also to discover some aspects of confinement, which is still considered a little bit mysterious. So how we do experiment, we study basically the deep inelastic scattering, semi-inclusive deep inelastic scattering. We have the electron beam in the Jefferson Lab, it interacts with a nucleon or with the quark inside the nucleon, inside the nuclei in the fixed target. We later detect using class 12 detector. I will talk about both hadrons. And this might be all the plethora of hadrons which might be produced and detected in JLab in the past and now in the future. Let's say. So as I mentioned in our experiment, we use different types of nuclei with different number of nucleons. This is again the same picture as before, but in a nuclei. And we believe that having high statistics, which is providing the class and class 12 provide, and having measured several observables, where we compare the heavy nuclei with a single nucleon, we can get some valuable information about the hadronization process in the nuclear medium. So I will talk about these observables we measure in the talk. But also I will rely on some theoretical model of hadronization, which is simplified some picture here. We have a virtual photon emitted by the electron. We have a quark, which is knocked out of the nucleon inside the nuclei. It starts to propagate in a medium, emitting gluons. And later it forms some kind of prehadronic stage, which might be related to the production of quark, antiquark, and after that, the final color field of the hadron is formed, and we see the final hadron which we detect. So there are two time scales which are typically related in the theoretical studies to this to hold the process. There are the prehadron production time, then the quark propagates in the nuclear medium, and after that, then prehadronic stage is formed and the final hadron is formed, is formation time. So There are many questions which arise, and I say it's directly also connected to the confinement, of course. Here we have again the picture with some theoretical model already incorporated in this illustration in a simple way. But for instance, one of the important questions which may arise, where actually hadronization happens, and even if it happens inside or outside the nuclear, or depending on the size of the nuclear, it may happen in both. So this is another type of question we try to answer. And many studies we may do. I will focus today in two observables, which are very significant. One of them is the transverse momentum broadening. So as I say, in the experiment, we use heavy nuclear, different type of heavy nuclear, but also we have a deuterium target. And deuterium target, we look at it as a combination of proton and neutron for the moment. So what we measure the PT square distribution on the heavy nuclear and take the average, and also after that the PT square distribution on the single nucleon, we take the average again. In both cases, the PT square is defined, the PT is defined on respect the direction of virtual photons. So we see like virtual photon, which is knocking out, like in your imagination, the quark, and the final hadron, in this case, the pion is formed. So the PT is this component in the original, in respect of the original direction of the virtual photon. So we take these two averages and see the difference. So this, we call this observable broadening, PT square broadening. The other important variable or observable is the hadronic multiplicity ratio, which is the ratio of number of the hadrons produced on the heavy nuclear to the same on the deuterium or the single nucleon, what we think. So basically, in this very original, old, simple understanding, this had to be equal to 1 because there was a belief that it doesn't matter if nucleon is inside or outside of nuclear, and if you destroy it, eventually the cross-section would be the same. But what actually is observed, starting from the Hermex experiments, that this is not 1. So it has some shape, and I will talk about the shape. So the advantages of the Jefferson lab, the CEBAF, and glass detector in particular, which is 4P detector, is that we can measure these observables, both observables, as a function of the 5 independent variables. I mentioned here the Z, which is the fraction of the energy of final hadron, which is carried from the original virtual photon energy. So it's a virtual photon original energy, which is passing to the final hadron. We have defined in the laboratory frame. Laboratory frame in JLab, we call the frame that the target is in the rest, basically. It's not collider experiment, just in case. We have also nu, which is the energy transfer from the electron to the hadronic system, or the proton in this case, or neutron inside the, again measured in laboratory frame, but PT square, which I already mentioned what it is, Q square, which is momentum transfer for momentum transfer, and the phi is the azimuthal angle of the final hadron produced on respect again of the direction of the virtual photon. Okay, our reference is the virtual photon for all these variables. So as I mentioned, our advantage is that we can do 5-dimensional measurements, and I mentioned the 5 dimensions only because we basically three variables. The 2 variables are the 2 degree of freedom of the electron. The 3rd degree of freedom is symmetric. The beam in experiment wasn't polarized. The target wasn't polarized, so we can ignore the 3rd, and the other 3 are corresponding to the hadron we measure. So similar studies were performed before, a little bit history, in Hermes, in DESI. So you can see here the Hermes results on the broadening as a function of A. A is an atomic number, basically, of the nuclear they measured. They did experiments on 4 types of nuclear target: helium, nitrogen, krypton, and xenon. And you can see here 3 types of hadrons they did. So what they observed is important, that the broadening basically is growing with the growing size of the nucleative important observation. They did also the same studies, the broadening studies as a function of nu, q square, z, pt, and in different kinematical ranges. So they did also two-fold measurements to have more like representation of the shape, the whole shape of the process. And here their results on a multiplicity, hadronic multiplicity ratio. Again, these are the same for nuclear targets. The heaviest one is the blue and the lightest one is the red. So helium, basically, you see it's like on the one. Yes, it's very close to, they compare it to the proton eventually. And the heaviest one has the highest attenuation. So basically, the cross section is very much suppressed for heavier nuclei. And the variables here again, nu, z, q square, pt. And they have also multi-dimensional measurements, two-dimensional, two-fold dimensional measurements. So this is from the Hermes. I will talk about the results from Jefferson Lab, which the measurements which were performed in 2000s with a glass detector, and the measurement which is going to be performed next year. Actually, it is scheduled still for January to end of March for 2024. So this is the Jefferson Labs CBAF 12 now accelerator with all 4 holes. The detector which where they do these studies is in the hole B. Currently it's class 12 detector. In the past it was a class detector with about 12. In the past it was a 6 GeV beam, and now it's a 12 GeV beam. We have also hole D here, the nucleic experiment. The J-Lab, you may know, it's in Virginia, in a historical significant part of for US history. This is the old class detector. The advantage of that, it was a 4P detector. It had it's like this. It has this onion structure. Has 4 types detectors from deep chambers to time of flight, Cherenkov's, and colorimeter, electromagnetic colorimeter. Everything in a magnetic field, so it's allowed to separate different type of hadrons depending also on their charge. So in the experiment, which was called had a name, it was called EG2 experiment. We used a special target. We called it double target. So what was the structure? The structure was that we had the cell with a liquid deuterium, which you can see here or here in the giant-free simulation. And in front of that, we had a solid target. And these solid targets during different round periods of the experiment were interchanged. So the one which was on beam was flipped off, the other was flipped on. And the beam was going through coming from here, going through the deuterium target, and later through the solid target. So we were getting data at the same time from nucleon, let's say, and from heavy nuclear. And we also used 6 types of nuclei. The data will show because of some technical issues, only 3 of nuclei got enough statistics there, the carbon, iron, and lead, and I will show them. There's less data for aluminum and tin. And so we used the liquid deuterium as a nucleon because we have the same proportion there of proton neutron. Yeah. And also the nuclear targets were selected the way that, for instance, we had the carbon 12, it's a 6 proton, 6 neutron, and iron 56, 28, 28. So the idea to have the same proportion of proton neutron and see if it matters. Of course, in the lab, this proportion is violated. We have the number of neutrons in much more than protons. So there were many studies performed with this data, and a part of the hadronization study in the nuclear medicine, about which I will talk mostly today. There was a color transparency studies, the short-range nuclear correlation. This one was pretty successful because it got several Nature and Science papers. 2πn correlation, dihydron suppression, etc. So it opens a lot of space for experimental studies. This is the kinematical region. Basically, we focus on the deep inelastic scattering region. So we have here the Q square and double V cuts, and also we remove some high Y, Bjorken Y region to remove very high radiative regions, which are affected by radiation of the photons by electrons. So this is the region where we focus. As you can see, also the double is invariant mass. We try to stay out of the resonance region, but still there is some contamination, of course. So this is the hadron multiplicity ratio integrated plot for charged pions. We have the positive pions, which are the blue points, and the negative pions, which are this orange, I would say, points. As you can see, it's as a function of Z for carbon, for iron, and for lead. This is the publication of these results, which was working my student, Sebastian Moran. You can see again the attenuation, which is increasing the Z, is getting bigger and bigger, depending on the size of the nuclear. So for lead, we have the largest attenuation, highest Z, and higher nuclear size, nuclear medium. Also, there are some fits of this data. Mostly, I would focus on the Jibu model, which is pretty complicated model with many factors involved. And we can see that Jibu is pretty much describing the data. Also, we have here Guyot-Gapilovich model, which is mostly a model based on the illustration I showed in the beginning of the talk. So it's a quark knocked out from the nucleon, propagating from the nuclear medium, emitting gluons. It's a gluon energy loss. After that, there's a prehadron formation, which has a smaller cross-section of interaction. And later, the final hadron is formed. So they did some calculations and mostly focusing on the so-called leading hadrons. Leading hadrons is the hadron which is carrying the knocked out part, the valence quark. And you can see the calculations also pretty much are describing the data. As I mentioned, we can measure these variables in manifold kinematical folds. This is a big advantage. So you basically make the life of theoreticians a bit more complicated on that. You can see here that, again, this is carbon, iron, and lead. You can see the different new regions here. This is energy transfer from the electron to the system, and also different Q-square regions, notably the different colors of the dots. Again, yes. Z is the energy of the hadron divided by the nu. So basically, nu is, you can imagine this way, the nu is the energy of virtual photon, and part of this energy is carried away by the hadron detected. So this is how much energy it took from the virtual photon. You can think this way in first approximation, yes. Excuse me? When it's one, yeah, one is basically, yes, that whole energy is going, yeah. Exactly. Again, you can do some conclusions here. For instance, the Q-square dependence you see is not so significant. It's more important, of course, there is some new dependence. And also you can see like anti-attenuation also for low Z region. And low Z also, we believe these are the hadrons which don't carry the knocked out quark or the valence quark. So again, this is the results for charged pions. We have also measured attenuation as a function of PT square. And here also there is an interesting result that basically for free nuclear target, carbon, iron, and lead, they see that we have attenuation until some values of PT square, and later it becomes like anti-attenuation. Basically, the cross section grows for very high PT square. We call it like I put it in this brackets, like Cronin effect, because there was a Cronin effect observed in Fermilab decades ago on the collisions. Similar, but what we see interestingly that yes, we have some increase for high PT square. And also this is directly related, of course, with the broadening. I will show you. Again, more information you can find in this paper. We have the different Z regions, and also we have fits from the JIBU, which work pretty much well. Now, the transverse momentum broadening, this is not published yet, but it will be published soon. So we have integrated case for the carbon, blue is the iron, and black is the lead. As we can see again, this is a broadening as a function of Z. We can see that again, the broadening is bigger, the bigger is the nuclear. And also it's becoming more important for higher Z, or maybe there is some plateauing starting from some value of Z. Okay, so carbon you see like even going down. So it's again question to discuss. So this is integrated for all variables. This is the same plot, but we put x Feynman greater than 0, and x Feynman just ensures that the hadron is, if you don't remember the definition of x Feynman, it's basically the longitudinal momentum of the hadron divided by the maximum possible momentum it can carry, just defined by the cinematics. And if it's positive, it means it goes forward, and if it's negative, it goes backward. And this observable is measured in the center of mass system. So basically, these hadrons, they go center of mass of the virtual photon with the hadron. It goes forward in the center of mass hadron. And we can see that this part like disappears, and we see more like linear plateauing eventually behavior for x Feynman greater than 0. So the same results again in different kinematical beings. Unfortunately, the letters are very small, but you can see different nu beings and different Q² beings. So this is the main advantage of the JLab and class compared to the Hermes. We have more statistics, and we can see more dimensions with very good statistics. Another variable we observed and we have very interesting results is also relating to induced energy loss studies in the nuclear medium. Basically, instead of detecting one hadron, we started to see in the same event several hadrons, and this way we construct a momentum vector. In this case, in this picture, in these illustrations for 3 hadrons, and see what happens. So I show only again just some preliminary results. This was worked out. The previous results were worked out. It was a work of my student Esteban Molina. This is Matias Barria. So basically, you can see again 3 nuclei. We can see 1 pion event and 2 pion events, positive pions. And what we see that basically the broadening is changing and it's becoming smaller if we have more. We have also results with very poor statistics for 3 pions, so I decided not to put it here. But again, here we have the carbon, iron, and lead, 1 pion and 2 pion. And this is blues are the 1 pion events, and the reds are 2 pion events. And as you can see, it's as a function of Z. Z is in this case is the fraction of energy which is carried by all hadrons, these 2 hadrons in the reaction. So we can see again that broadening is suppressed in comparison. Then we have only 1 pion events. We do all corrections also to ensure that we have really 1 pion produced or 2 pions produced. These are now results for neutral pions, pi zeros. This is the work of Taisia Mineva, and this one is going to be published soon. it already has a approved analysis node. Actually, one of the committee members is here who was approving it. So we have here the multiplicity ratio as a function of z. Again, for different, these many points, they correspond different kinematical regions. Again, we see the results for carbon, for iron, and for lead, which is the separation is bigger. I didn't put it together with charged pions, but the attenuation is less than in charged pions. This is interesting result. And also you can see the broadening as a function of multiplicity ratio as a function of pt square. Again, we see this so-called what we call Cronin effect for high pt square. Again, in different kinematical regions and for different types of targets. There is an interesting thing that this anti-attenuation is for charged pion, it's bigger for lighter nucleus and smaller for heavier nucleus, but in case of pi zero, it's vice versa. It turns over, and we check it a lot, and it seems like it's the case. Also, we have some data with much less statistics on eta and omegas. You can see here this multiplicity ratio integrated as a function of z, but now you see that errors are getting much more significant because we are reaching in class to the kinematical region, then we can produce really heavy hadrons. This is another interesting study, which is we are also able to observe different types of correlations between the hadrons. And this is the dihadron azimuthal correlation. This is published in this paper. Again, it came out last year. And what we see, I won't, because of the time, I won't stop on that a lot. But what we see basically that we don't, if there are two hadrons and they are in the same, they are produced in the same direction, we don't see really attenuation, but then they are in 180 degree, the attenuation is maximum. So this is again, this is fitted by the GBU. You can see results here, and it gives some description from the GBU. If you look in the model, it's related basically with production of hadrons inside the nucleus or in the surface, the final hadron of the. This is also another result. This is not published yet. Two pion correlations. We basically using some techniques which the back Bose-Einstein correlation we can study, which came from HBT, which is coming from the astronomy. Then use two sources of the light to define the size of some astronomical objects. We can also use the same techniques to define the size of the area that the nuclear final hadron was produced. This is studies which are also heavily done in ALICE detector, where they have also the opportunities to look at these correlations. So a little bit about the future. So as I mentioned, next year we will have the same experiment, but with higher energies and higher luminosity and higher statistics and higher variety of the hadrons to measure in the class 12. Now with above 12 accelerators. So this is the class 12, which is now built inside the whole beam. We will have much wider cinematical region to study, and also, as you can see, also the W is going now up to 18 W square. Before if I remind, we were staying like here. So we are really getting far from the resonance region, and this is important for us. Also, we will have a wider range on Q square, on nu. So, and this will allow to observe much wider variety of hadrons. So we haven't, I didn't show everything, but we have published data for kaons, for positive, negative pions, for neutral pions. We have studies for eta, for omega, but with And also there are some published data for lambda, and we have studies for protons. But with class 12, this range of particles will be much wider. And statistically it will be much better also. So the experiment will happen next year in the first semester, most probably. It's not clear. It's from January to March or from the March to May. So for that, we built another target similar to the previous one, the dual target. It was completely designed and built in Santa Maria in our university with our engineers. So to build the target, we had to overcome several technical complications, and mostly because in the new class 12 design, the space to put any target is very reduced. We should, of course, use high vacuum. The previous target wasn't in the magnetic field. Now there's a solenoid magnetic field of 5 Tesla, and we still need to produce some movement. This was also an issue, and we solved it. We of course use some electronics, but which is not traditional. So we use piezo motors in order to avoid any kind of iron inside the magnetic field. Cryogenic temperatures and high beams. So the target is already ready. This is the design. But again, the beam will go through the deuterium target and will cross the solid target. And you can see the solid targets. There is a piezo motor which will move these bands. They are on the band. It will move to right and left and right, and will take data on different type of nuclear targets. So 30 pack days, that means 2 months of running is planned for the next year, and another 60 days in 2025. This is now how it is scheduled for the moment. These are the targets we will use: deuterium, carbon, aluminum, copper, tin, and lead. Unfortunately, we can't use iron because there is a 5 Tesla magnetic field. So we decided to replace it with copper. And this is some photo of the new target. It doesn't have the cryo target inside. The cryo target now is finishing building in JLab, and we finished this one. This is design. Again, it will be cryo target here, the beam going through it. And some conclusions. So we had like wide variety of studies on the old experiment, in EG2 experiment. And we measured different processes and observables. The same experiment is going to be repeated. It's now called class 12 RG experiment, round group E experiment. And also an important remark that all these studies, of course, they go to the future because they are included in the EIC program. And also there are some plans on JLab upgrade, 12 GB, and of course we will benefit on that also if it happens. So thank you very much. So.
Are there any questions?
Thank you for the talk. So I have a question on the 2-pion Bose-Einstein condensation results. There was a red line there. Is it a fit or a model?
It's a fit. Yeah, yes, the red line is just fit. But the function we took from some theoretical paper, I don't remember now the authors exactly which function, but it's a theoretical model which is used by Alice mostly. Yeah. I didn't put the numbers, and I don't want to say something which is not in the top of my head. But I can share with you the more slides. Okay. Yeah. You can but by this you can it's better if I show, because there is a function which Alice uses. We fit it and we get some parameters, and also we did 2-dimensional measurements. Only pi plus for a moment. Yes, but we can do also for pi minus. This is a work on progress. That's why I didn't go. But yeah, we have also there are 2-dimensional, so it's a transversal size, longitudinal size, and there is a shape also which is predicted, not circular but more elliptic. So we have the numbers, but it's better if I share you by email. I don't want to say because I have some numbers, but it's better not.
Hi. So thank you for the nice talk. I have a kind of general question. So I had the impression when you showed comparisons to theory, when you were considering different nuclei, that the heavier the nuclei, the worse the result from theory was. If that is true, do you have an understanding why is that?
Yeah, in JIBU, yeah, exactly. It's a very good observation, exactly. So let's say even this look here. Yes, the lead is failing, yes, from JIBU, for instance. And one of the reasons it might be is related again because of this disproportional proton-neutron. This might be a reason, because exactly as I said, in all targets we have the same proportional proton-neutron, except lead, then it's higher. So this is the first thing which comes to the mind. But this should be worked out more seriously. Yeah.
I'm curious with 2 points. One, you have shown the 2 pions that you measured in correlation. I mean,
this one, or
yes. So you see an increase. You have as a function of z, and then you also show the result as a function of the mass of the 2 pions.
Yeah, this is the hádron studies. Yes.
Yeah.
This one, yes.
Yes.
Yeah,
and then you have this increase of the. So you see the resonances or what? No, on the when you increase the mass of the subsystem.
Missing mass. No, we don't think it's a resonance. It's just basically correlated to this also. So
I was interested in the final state interaction between the 2 pions, if you can see some indication of that or not.
So this is one of the results which is interesting. So I can give you 100% answer now why it happens. Again, the interesting part that the JIBU basically observed the same. And this is one of the explanations from the JIBU is that it's much related to the fact, as I said, it's also related to this attenuation, then they are backwards. So the fact is if the hadrons are produced inside or in the surface of the nuclei. So you can do some kinematical calculations and you could observe it. But this again requires more analysis.
You do not separate when the center of mass of the 2 pions has a very large PT. And then you look to this dependence.
No.
You don't do that.
No.
Yeah, because probably for the large PT, you can see the 2 pions interacting, and then there was my other question.
Yes.
If we can see 3 pions.
Yeah,
as well.
it's a good point, but again, look, even I will show you here. Unfortunately, these 2 pions, with 1 pion we are very good in statistics. But we go to pions, it goes down. 3 is very low, and also when you go to pions, especially in these regions, when you say you can say high PTs only, it's going down. So you can't. Yeah, it's going down. So you can't do really good studies with good errors in that region. But with class 12, it will be possible. Yeah. So
Thank you very much.
thank you.
Okay, and the next one, let's see. Somebody's doing this well. Good. Okay, our next speaker is Chung Ji, and he's going to talk about the bridge between QCD and light front quantum mechanics.
Okay, good morning. we're discussing a lot of interesting phenomena and many very interesting experimental data coming up, and it will come. So we would like to understand those experimental data from the theory. And so I'm going to talk a little bit more fundamentals of the QCD and the connection to sort of phenomenological quark models that have been discussed in this conference. So typically we understand the atoms fundamentally from quantum electrodynamics. So atomic model and the quantum electrodynamics, the bridge between the two seems very strong, and we seem to understand very well. But the bridge between this quantum chromodynamics with the quark model is still, we are struggling to make some connections. And the reason behind that is, of course, color confinement. It's very different from the connections in the atomic model with the QED. So that's the sort of motivation to discuss about this and how we may try to do. So I would like to discuss a little bit of some fundamentals using the well-known toy model called the two-hoofed model. But essential thing is that we know that the QCD quark mass is very small. However, this proton and neutron nucleon mass is much higher. And so we understand the origin of mass of the universe is mostly from strong interactions rather than the Higgs mechanisms. And also this pion is a very interesting particle that has been discussed in this conference as a Goldstone boson, and it has a dichotomy of, in terms of quark model, it's like a QQ bar system, but pion has a very interesting property based on this QCD of global symmetries. So we'd like to understand these things and seeking some model calculations and so on. So it looks to me that the 1+1 dimensional QCD is great to start, and to hope to utilize this NC goes to infinity technique to come up with this two-hoofed model. So this is a very good toy version of QCD to discuss most of the things that we are talking. What I noticed was that this two-hoofed model, people can study so-called the instant form dynamics, ordinary instant time, but also in terms of the light-run dynamics. And that's actually two-hoofed did from the beginning. He was able to solve this model utilizing the advantage of this light-run dynamics, especially it's a 1+1 dimension, which doesn't involve any rotation. So therefore, it maximizes the advantage of the light-run dynamics. That's the reason he was able to do. But then later on, instant form dynamics, people want to understand, so several people actually try to solve numerically and so on. And in the first day, of course, we had a discussion about the treacherous points of this light-run dynamics and so on. So I thought that it would be a good idea to make a connection between instant form dynamics and the light form dynamics some way, and understand all these treacherous points more explicitly. And fortunately for this two-hoofed model, we were able to do it. So that's just something that I want to show. A little bit of history and what's the main thing we achieved. But there is a lot of more things have to be done, okay? But at least I think I'm very happy that we are starting and beginning on this effort. So after talking about a little bit of history, I will show these mass gap solutions in two-hoofed model, in interpolating dynamics, and also spontaneous breaking of chiral symmetry, measure spectroscopy and wave functions. So spectroscopy and the wave function related physical observable both have to be consistently be shown. It actually agreed with the experimental data and so on. And as we have seen in this conference, still that has not been done. Okay, separately, people to discuss. And then I will just make some remark about this application to hadron physics with this interpolating method. So this large NC QCD two-hoofed model is essentially the same Lagrangian as you see here. It involves two mass scales because of 1+1 dimension characteristic. So of course, the mass you introduce in the Lagrangian, but also the so-called coupling has dimensions, so that typically that G goes to 0, but NC goes to infinity, that this so-called two-hoofed coupling lambda has a mass square dimensions. And I think some of the talk in the conference discuss about that. So Dirac proposed, and this type of slide has been shown a few times in this conference, so I don't have to go through too much. But essentially the upshot of this thing is that this light from energy and momentum are combinations of this equal time and so on. So really what we are discussing is that it's not just this coordinate transformation, but you want to have the degrees of freedom. You want to have an equal time degree of freedom or equal light from time degree of freedom. Those are the two different things. So 1 degree of freedom here could mean that the many degrees of freedom for the others and so on. Okay, so those are the very important thing. So in the first day, there has been some discussions about this light from 0 mode, and in 1+1 dimension, really the thing is that, you know, particles can go front and backwards and so on. But in the light from dynamics, with this light from time, it's essentially going only forward. There's no backward, but it can stop. So that's the sort of the essence. So I just to summarize several references. Still, this is quite short, but in particular, the ones which uses the light from dynamics LFDs are shown here. And then also there is IFD effort, even more recently, using these moving frames to discuss about quasi-PDFs and so on. So I'm going to actually mention about those things. But the first attempt to really connect the light from dynamics and the instant form dynamics was Isaac Frischmann et al. Was trying to do it, interpolating gauge, so-called the axial gauge to the light from gauge. However, they just did only the gauge boson sector. So therefore, they find some inconsistency and so on. But that motivated us. And then eventually we did entirely. If you do it, there is no inconsistency. And then you can actually able to do this. So Pei-Ling Ma is my former graduate student. She did a good job, and she actually is the postdoc at Argonne National Lab. So a little bit of history on interpolation is that we have been really trying to do this connection between the equal time degree of freedom and equal light from time degree of freedom, and then interpolating that with some interpolation parameter. This was actually introduced by other people like Isaac Schrichman and so on, but Ken Hornbosser was really the first one who had a seminal paper on this, especially focusing on 1+1, some model Lagrangians and so on. Unfortunately, he passed away several years ago. I had an overlap at Stanford, had a good discussions. But I noticed that since then, there were no real effort to follow up on this approach. So at NC State, I was trying to do so. So I was able to do a few things that shown here. And eventually we were able to do some gauge theories, and then 3+1 dimension QED could be done. And then we recently did this QCD 1+1. So this year, somehow Springer was interested in putting this as a book. So fortunately, it came out rather recently. So the idea of this two-hoofed model is that we are trying to use this so-called interpolating axial gauge, which connects between the instant form axial gauge to the light form gauge. So all these hat notations that you see, that was something that I invented to show the this interpolating so-called dynamics. So whenever you see these hat notations, it has some delta informations. And so the first thing we wanted to follow up was this mass gap equations, and that has been discussed already in this conference. But this is where this the beauty of two-hoofed model comes in because of the large NC limit. So you don't have all these overlapping non-topological diagrams, but it's essentially given by these planar diagrams, and that will give the exact answers. So in this sense, I think QCD is a little bit simpler than QED. Schwinger model could be done, but it's almost horrendous to do it because of all these overlapping non-planar diagrams, etc. But anyway, in two-hoofed model, it can be done exactly. And one can have this iterative equations. And these equations can be diagrammatically shown as this self-energy Bethe-Salpeter type of equations. However, it can be derived a couple of other ways, algebraically, starting from Lagrangian, minimize the vacuum, etc., and so on. So it's all consistent. It comes to the same equations. So the solution of this eventually can be summarized in this fermion propagator. So the free fermion propagator is very well known like this, but when the particle is interacting with gluons and so on with non-trivial vacuum, then the form of the propagator is shifted with this so-called self-energy, which has a so-called scalar part and the vector part, two parts. So it can be summarized into so-called this renormalized mass function. And quite importantly, there is this wave function renormalization factor has to come in together. And we noticed that in two-modal discussions, people talk a lot about this renormalized mass functions, but not really the wave function renormalization factor. We found that's very crucial to include it. So this was something that we think we did the first time. So by putting this together, one can find this energy momentum dispersion, and that energy momentum dispersion in relativistic particles can be summarized by this triangle, essentially. Even free particles satisfy. So you have some mass and the momentum, then this side will be given by energy, square root of m squared pg squared, things like that. And this angle between the energy and mass is related to so-called rapidity. This is very well understood, of course, in the free particles. But when the particle has an interactions, it's non-trivial interactions, it still keeps the triangle shape. But it's interesting to look at this angle has a free part, but also it has a so-called Bogoliubov angle, which comes in, which connects so-called free vacuum with the non-trivial condensed vacuum, etc. So that's the quite important things. So with that, you can actually find this energy function with this mass functions, but this result has to include this wave function renormalization factor with this ordinary energy and so on. And that actually solved some of the puzzle, that previous work that I'm not going to talk too much, but previously there was some interesting things that they just put it under the rug. But now I think we can clearly understand those things. So this mass gap equation with the interpolation angle. So this capital C is just cosine 2 delta. So it between 0 and 1. And it actually can be written something like these two equations, because indicating that scalar and vector part of the equations. But it can be scaled with these energy units. So here everything could be dimensionless quantities, and also it can be also scaled with this interpolation angle. So you can see that the whole equation can be summarized universally in this way, no matter what angle you choose. So that indicates that the solution of this mass gap should be independent of the interpolation angle, as one may expect. So here's the solution. This is actually a numerical solution. And it just shows essentially for, in this case, original mass equals 0 case, then this dispersion is very simple. As you know, the energy and momentum is just linear. But then many different angles that you can try, but you can actually see it all agrees with this mass gap solutions. So therefore, one can see that what people so-called saying about the constituent quark can be interpreted as this mass gap from 0 to that. So all these constituent mass can be summarized with different masses here. And you notice that there is a corresponding wave function renormalization factor. And very interestingly, there is some sign flip comes with m equal to 0.56, which is actually 1/√pi is analytic result. So that's where it is. And for different masses, you can get, of course, very similar type of all the mass gap solutions. So after finding these single particles, the mass gap and so on, we can try to build up the meson system. So it's like a QQ bar system that we can have. And that satisfies this Bethe-Salpeter equation. Sometimes the jargon is Dyson-Schwinger equations. But anyway, it actually has this, again, utilizing this planar diagram is exact here. So one can solve exactly this type of equation. The basic story is that you have this so-called forward moving and the backward moving, they are coupled. So there is a phi plus and phi minus, those are the forward and backward, and they are coupled in general. But here is a very interesting thing. If you actually let the interpolation angle going into the light front limit, then lo and behold, all these minus part, the backward one, goes to 0. And then only the forward one comes. So this coupled equation becomes just a simple one equation. And this is a dramatic change and advantage here. And this is really giving some hint of this connection from complicated QCD fundamental dynamics to the light front quark model type of a theory. So in fact, this outcome here is very much like just the ordinary light front bound state equations. Okay, so that's the sort of very interesting link one can find. So after that, we just solve it. Of course, there are some results, but these are all done with all different interpolation angle. It doesn't matter, it always agree. And then it actually gives the nice connection between the 't Hooft original, this Regge trajectory, but also Ming-Lee's rest frame result, or more recently, the moving frame with YGR et al. And they all agree. And here is, for the fun, we have this dotted line, which mimics the really the pion. Of course, m equals 0 will be the chiral limit of pion, but it's very close. And you can see all these Regge trajectories. We have also done this chiral condensate, and there is some exact result by Ariel Chitiniske, the m equals 0, and then Matthias Burkhardt had all the other mass analytic form, and the numerical result just reproduce all of that. And the so-called Gelman-Oaks-Renner relations can be tested here, and it pretty much agrees with the numerical result. And this is the 1+1 version of that. And then once you have a spectroscopy, you can also find the corresponding bound state wave function. So here is the exact bound state wave functions, m equals 0 case one can find, and analytically it's given, and it works for all interpolation angles. And here are some results for different angles here. This is the instant form dynamics. You can still see that some result here, which is rather different from the real result here, which should be something like just a box, positive energy and negative energy must be 0 and so on. So what's shown here is that you just change the center of mass momentum. So you just change the momentum, and one can actually do that by doing so. And then momentum gets increased, then looks like these nonsensical results becomes more like a light front box shape of result, and the negative energy also goes down close to 0 and so on. But what we found was that you don't have to really push this momentum too high, what you can do also is that you can change this interpolation angle, gets close to the light front, okay? So you have another leverage to do it. And then if you do it, then you can more quickly going into the light front ones. So this was the idea that we could apply this so-called quasi-PDF idea. So typically in instant form dynamics, they introduce this quasi-PDF idea, trying to mimic this exact, the light front A plus equals 0 quasi-PDF, but we were able to do it for any interpolation angle here. So the difference is that in instant form dynamics, you really want to push this momentum very, very high, but that causes a lot of difficulty discussed in this conference in the lattice calculations and so on. But this way, maybe it solves some of the issues they have. So here's the example that quasi-PDF. So in exact light front dynamics is like this square boxes in here. And these are the different momentum they try to obtain, but they go very, very large momentum here, but it's still not quite giving the exact result. But is in comparison in our approach, we don't really, these are the boost values. So we actually see that you didn't boost too much. It's like 1.76 is like between the two in here. However, what you can do is that instead you change this interpolation angle, then you can see that without too much boost, you can get very close to the exact result. And then hope that this type of thing can be really realized in the lattice. And I think we can, in principle. And so I have discussed with Michael Engelhardt and so on. They were interested in, but at the moment they're tied up with some other business. But it will be very interesting. People pay attention to this and then do some real calculations. So here is the some idea of so-called weak rotation with this interpolated momentum and energy, and I think it's doable. So the conclusion here is that QCD 1+1 large NC Tooth model, it seems that now we have a much more handle on it, and we can interpolate between instant and light front dynamics. And then all the things people talk about, this chiral condensate measurement mass spectroscopy, rede trajectories, Gell-Mann-Oaks-Renner relations, and all those things with this non-trivial vacuum phenomena are preserved no matter where it is. And we find that this so-called alternative quasi-PDF idea, having these two parameters that you can fiddle, one can find some sweet spot to really mimic the light done in the lattice. I'm not really an expert, so I'm talking with some of the lattice experts about this. And of course, obviously, this last point is very important. The interpolation of a real QCD 3+1 NC = 3 is, of course, needed, especially, I think, the real essential question that we have to address is how this mass gap solution look like in the time-like regions, okay? So people discuss a lot in the space-like regions, but really what's happening? You don't find any unmasked shell quark, right? But you pretend you have an unmasked shell quark and then do the calculation anyway. But I think in this type of work, we build the real fundamental approach to all these things. Thank you.
Very nice, Chung. We have time for maybe 2 quick questions. Tobias?
Exactly about this last point.
And this is why I think even in QED, of course, we can just do it perturbation there. But if you really try to do non-perturbative calculation, some of the people are trying to do here, has a, depending on how you do it, somehow your result come out differently. That's indicating how important those effects are. So in some sense, QED is much more difficult in a way, but here at least you have a handle.
No 1 over NC, right?
Right. We need 1 over NC. So that's the thing. It's a very important. So we have to do one by one. First, you can do large NC limit, and then you try to accommodate these transverse directions to make a 3+1. So that I think is rather doable, and then that it could be more straightforward. But then the real question with how this 1 over NC plays the role, and that will come later. Some of the calculations people showed was that they think that NC equals 3 is almost like infinity. I don't know. Yeah. That's the, all right.
Next, right? Oh.
Yeah, I know.
Yeah, you have a question?
Okay. Thank you very much, Professor G, for this very illuminating talk. I have a question. So is it possible to derive a effective lifelong QCD Hamiltonian or simpler lifelong effective Hamiltonian using this interpolating method to incorporate, for example, the zero modes and other physics that is otherwise not available in the canonical lifelong Hamiltonian that we have?
Yeah, so as I showed that in this slide, which actually makes some link, doesn't go back. But anyway, you remember that there was this coupled equations of the forward and backward moving boundary state equations are coupled there, but in the lifelong limit, that thing is reduced down to ordinary lifelong quark model type of equations. And these lifelong type of quark model result can be connected to what you're talking about, this effective Hamiltonian approach, PLFQ or any others. But I think in this 1+1 case, it's much, in some sense, simpler, and it can be done more or less exactly. So this, I think, yeah, one can derive those things, and people have done it. In fact, Ken Hornbosel a long time ago in his thesis doing this DLCQ approach before PLFQ, of course, and they got pretty good result. And what we are finding is it all connects to that type of previous result.
Right. So with the derivation you mentioned, in particular, Hornbosel result, is that for 1+1 dimensional, or it's also easily extendable to 3+1? Because I know that the TÜV model, the vacuum property of TÜV model is shown to be simple, relatively simple, but
it has all the features that people talk about, like chiral condensate and so on. Of course,
right.
Talk about how these instanton solutions that exist in 3+1 will come in, and that will be the major things that we have to discuss in the extension in 3+1. So, in some sense, understanding this instanton effect in the Minkowski space is a very important issue, and I'm hoping that this type of approach could reveal, how we can do it. We haven't done it, but of course we are working on it.
Okay, I think we need to move on. So if there's any more questions, we
Thank you.
can come up during the coffee break, okay? Very nice. Okay, our next speaker is Eduardo Fraga, and he-
Oh, yes.
Oh.
Sorry.
Oh, sorry. Next speaker is Eduardo Fraga, and he's going to talk about hot perturbative QCD in a very strong magnetic field background.
Thank you.
Can you hear me? Yeah. So first of all, I'd like to thank the organizers for the opportunity. And I'll kind of try to make the session even more eclectic, right? So we had experiments in JLab and large NC, and I'll have PQCD in large magnetic fields, so totally different. Although I have a quick mention of large NC actually in one of my slides. So what I'd like to talk about to you today is a very extreme situation in which we have matter, strongly interacting matter, under the influence of very high magnetic fields, right? So in particular, I'm going to address, so how does it work? This should be the laser, no? Well, this is so fast, right? No, the laser is this one? Yeah. Oh, okay. No, it takes a second to appear, so, okay. So, so it's going to be hot perturbative QCD in a very, very strong magnetic background. And I think it's going to be clear what I mean by very strong is the largest magnetic fields you can find in the universe so far, and we are going to consider even larger fields than that. So there's a strong motivation to pursue this kind of question here in medium strong interactions on the extreme magnetic fields. First of all, are of experimental relevance. In high energy heavy-ion colliders in the early universe, where you have the thermal piece, so thermal QCD in high magnetic fields, but also in magnetars, if you go to high densities, and then you have in the stars very high magnetic fields. So you want to know how strong interactions behave in this kind of situation, right? In this kind of environment. So second, there's a very rich new phenomenology that came about. First, there was a ferromagnetic effect a long time ago and still trying to be found by several people. There's this new QCD phase diagram, since now you have a new external parameter, external control parameter besides temperature and chemical potentials, different kind of chemical potentials and so on. Now we can turn the magnetic field and see what happens. Actually, now people are turning the electric field too. So external electric field too, and finding a phase diagram more recently. So modifications for the vacuum and superconductivity in the vacuum and so on. So it's also amenable to lattice simulations, which is very nice. So you can compare, right, and test models and test theory and so on. So it's this new open channel for comparison in general. So it's model constraining, you can test PQCD and non-perturbative methods and so on. So that all seems very nice, but there is a problem, of course. However, right, so these two items here, these are the real deal, right? You want to describe experimental data, you want to find new phenomenology and so on that is measurable, but in this side here, you have very, very hard problems to face, because usually you cannot compute with reasonable control over approximations and over your hypothesis in this region, which is the more interesting. On the other hand, here we can play, right? If we go for lattice simulations, you can go to very high magnetic fields, you can go to very high temperatures in principle. So you can play with models, you can play with perturbative QCD and so on, as I hope to be clear in a few slides. So, okay, so a very quick slide on this. So from this thing here, what happens is a very, very short summary of what happened during like 10 years or so. So there were several effective models that started to appear in the very beginning of that. And they had predictions and everybody was happy until a certain point where they all failed, right? All effective models essentially failed when lattice results came, controllable lattice results. The first lattice results were kind of in a good direction for these models, but at some point, all the predictions were wrong, right? So then you can fix the models and try to adjust and include things and so on and so forth. But from my point of view, you have a failure of effective chiral models. So it's a very long story, and I can go through if people are interested in coffee break and so on. So then at the time, we decided to do something else. So let's try something else, right? So one thing that we tried with Letícia Palhares, who is sitting in the audience here a long time ago, was a bag model, which is even simpler than chiral models. And surprisingly, it was good, right? Good qualitative results were obtained at this time, but it's kind of puzzling and hard to justify by itself, right? I want to come back, not in this talk, but I want to come back and justify these results in the near future, hopefully. Then we also tried large N, right? So that's my reference to large N. That's done also with Letícia Palhares and Jorge Noronha. And again, we had good qualitative results. That's QCD in that limit. Oh, sorry. Oh. Something went wrong there. Yeah, so maybe the internet is oscillating. Okay. So again, here, this is different from the chiral models and different from the bag model because this is QCD in that limit, right? So this is a real theory. And then we also got good qualitative results, and still it's hard to get more quantitative and to improve and so on. But so then at the time we went to a third possibility, which is magnetic perturbative QCD. And that was done with these people here, again, with Letícia Palhares and Jean-Paul Blaiseau. And that's, again, is QCD in that limit. It's systematic and controllable, right? So you can perform approximations with control over your errors and so on. But it needs really, really high B fields. So actually, one needs this kind of hierarchy of scales. So you need to have like square root of EB in units of MEV or GeV or whatever you want. Much larger than the temperature, which is much larger than the typical mass, which is a strange mass, which is the largest one in this case, right? So that was the situation then. And at the time, like in 2015, there were the first very exciting results coming from the lattice. There were many results previously with respect to that, coming from the lattice, a phase diagram, and so on. But these were the first results at extremely large magnetic fields. So that was very exciting, this result by Gergo Andrade in 2015. And there were, I mean, pioneering results because it had really stretched to go to such a high magnetic fields, right? So the magnet in JLab, for instance, is like tiny magnetic field comparatively, right? So this is really huge, right? And so there was a prediction of a possible first order line appearing because if you don't have very large fields, you have a crossover, which is kind of boring. But then there was a prediction of a first order line, and then there should be a critical point. So that was a time where the first predictions came for very large fields. And then almost 10 years afterwards, so it was like last year, some results from this year, the PISA group found very interesting results, and they kind of started building this new phase diagram, moving to very, very large magnetic fields. So if you see from the previous slides, I don't know if it is written here, but it's something like 3 point something, yeah, here, 3 point something GeV squared, the maximum magnetic field that they could achieve. And for the PISA group, they could go to 4 to compare essentially, and then to 9, which is, yeah, here, it's written here. So not quite this situation yet, but we can play. Now we can try to compare with perturbation theory more or less reliably. Okay, so then again, besides lattice, what can one do from first principles? So perturbation theory is the answer. So you can do perturbation theory to order G squared using a non-perturbative magnetic background. So we're going to use an exact quark propagator in the presence of a constant magnetic field, right? So that was done a long time ago by Schwinger, and that was also formulated in a more appropriate way by Chodos and other MIT people in a way that one can do perturbation theory more easily. So, and we can all, of course, keep glue interaction to the same order and so on. So that was the plan. So the basic ingredients are laid here by Schwinger and by Chodos. So you can express the propagator as a sum in this form. It is more amenable for perturbation theory. And then you can compute the thermodynamic potential, which is something that looks like this bunch of diagrams here. So this bunch of diagrams are all calculable. The hard one is this one here, is the exchange diagram, which is the one that was computed. And one needs to be more careful with that. So if you express this in a sort of schematic way, you can relate this diagram to a much simpler one, which is a exchange contribution in 2 dimensions for hot QCD with a sort of massive gluon. There's a transverse mass that appears for the gluon, which is this guy sitting here. You can think of this guy as m squared, right? M transverse squared over 2 QFB. QF being the charge of the appropriate flavor here, right? So you have to compute this thing is the sort of average of over this gluon transverse mass, right? So the results that we had at the time showed clear dimensional reduction in the quark dynamics, as can be seen from this picture, so to speak here. There are no UV divergences here. And in this 1 + 1, the direct trace is proportional to the quark mass. Actually, it appears as a square quark mass. So that signaled a trivial chiral limit. So in fact, we can write the contribution to the pressure from the exchange diagram in this fashion here. And you can see, besides like some trivial prefactors here, m squared. And then there are these ugly integrals to be performed. Some integrals as Matsubara, some that were already performed here, actually. So I have to sum over Matsubara frequencies. You have to sum over Landau levels. It's a bunch of steps that one has to make, and plus momentum integrals to be performed, right? So it's actually very evil infrared divergence sum integrals to deal with. Very nasty, nested infrared divergence. It's really evil, right? But one can show that this next leading order is always 1 to 2 orders of magnitude below the leading contribution. So they're small, really small. That's true only for very high fields, right? So in principle, that should signal improvement in the convergence of the perturbative series at high T and extremely large B. Is that so? It's yet to be shown, I mean, with more terms, right? So no infrared divergence because there is this trivial chiral limit, which is guaranteed by the m squared in front of the integrals, right? It kills the divergences that are inside, hidden in the integrals are lots of log divergences, as we can try to test, right? One can do some semi-analytic and very extreme limits for high mu and low temperature and see the logs appearing there. So at the time, like 10 years ago, we had no running coupling, no running mass, no bands, no other observables besides the pressure, and no test for ultra high B fields. So that's the picture 10 years ago, right? So 10 years later, so like this here, revisited magnetic PQCD with Leticia Palhares and Tulio Restrepo, a postdoc in my university, with a running coupling, running mass, bands, dependence on the choice of the randomization scale. We'll see that there are several proposals in the market. So we tested, the most representative of them. And we computed, again, the pressure a little different way, the quark condensate, which was computed on the lattice, and the strange quark number susceptibility, which was also computed on the lattice and were not before for very large fields. And so we could perform some tests for ultra high B fields, reached in quotation marks because, well, high, but not as high as we wanted them to be. So we're kind of close to this situation here, but still not in the sweet spot. Okay, very good. So differently from what we did in, 10 years ago, we noticed that it's more convenient to perform the momentum integrals first and then leave one integral over this transverse mass and the Matsubara sums to the end, right? That's valid only for vanishing chemical potentials, but that's what we're doing here at the moment, right? So in the lowest Landau level limit, which we can take in the very high magnetic field limit, so the exchange contribution to the pressure has this appearance here. So I'm defining all these energies here. There's a sum over Landau level, sum over Matsubara frequency. So everybody is defined here. So in principle, we can compute this numerically. We also need the leading order for quarks. So it has this kind of appearance here. So this XF I didn't define here, but essentially MF squared over EB, or the root of it. I don't remember. I think it's MF squared over EB, which is dimensionless. And you have the log of this. And then you have the thermal integral that appears here. But notice that you have like a sum here of our flavors and one-dimensional integrals to perform, right? Because we're in this limit of very, very high fields. Okay, and you also need the contribution from the gluons that are blind to the magnetic field, and we do this again to 2 loops. Okay, so that's the ingredients we have for computing the pressure. We can also compute the chiral condensate, which is defined here. So you can take this as a derivative of the pressure with respect to the mass, right? So we have a contribution from the free part and a contribution from the exchange. So if we had no quarks, if we had no quark mass, this would be the true order parameter for the chiral transition. We have masses for the quarks, but it's still a pseudo order parameter, which varies a lot. So it's useful for looking at the phase transition or pseudo phase transition that one has for the chiral symmetry. And you can perform a perturbative analysis, which is reliable only for very large T and even larger B. So we cannot bring any information near the crossover or the phase transition. Of course, within perturbation theory doesn't see anything about phase transitions, right? So we can compute, it's perturbative, right? Phase transitions are non-perturbative animals, right? So nevertheless, so there are lattice results for very high T and B. So we can compare the 2 fundamental theory ways of computing things in a given region, right? And see if they're in the same ballpark. So that's the idea, right? So from magnetic PQCD, we have the contribution from the free part and the contribution from the exchange, which is this piece here, which we can compute numerically and then compare to the lattice. Okay, so on the lattice, one computes actually this so-called F flavor renormalized condensate, essentially to eliminate this additive and the multiplicative divergences. You're essentially subtracting the vacuum part here from this medium part. So we kill a lot of divergences when you do this, right? So, but recall that, and this is a very important remark, we cannot obtain the vacuum condensate. We cannot simply take the zero field limit. We don't have this guy here. We cannot have this guy here because we cannot make the zero field limit, because our assumption from the very beginning is that B is very large. So it makes no sense at all. Look at our results and ask, what happens for small b? It's a meaningless question for our equations, right? You cannot ask this question. So we simply don't have this guy here. So you're going to miss it, right? But still, if B and T are large enough, this shouldn't matter that much, which is not totally true, because B is not as large as we want, and T is even less than we want. And so again, we can move on and compute a different observable tool, which is a strange quark number susceptibility, which is this guy here. So here we have a derivative with respect to the chemical potential. So these pure vacuum terms are killed, which is good for us, right? So we're killing guys which would look like contributions of this sort here. So this is more advantageous when comparing to lattice simulations, but still the lattice is not the sweet spot for us yet. Okay, so let's go. So we also have running, right? So we have running of the coupling to the number of loops we're computing, and we have running of the strange quark mass to the number of loops we're computing. And again, the beta function coefficients are all defined here. And the lambda ms part for 2 plus 1, the ms hat for 2 plus 1, all the numbers are set here, details in the paper. So there is some arbitrariness in choosing the renormalization scale, which is this guy here, lambda bar, right? So in principle, we don't know how to choose it in general, in any place, in any situation, in the vacuum, for finite temperature, for finite view, it doesn't matter. We don't know exactly how to choose it. For thermal QCD, the usual thermal QCD with no magnetic field, nothing. So besides quark masses, the only scale is temperature, which is usually much larger than the mass, if you're doing perturbation theory reliably, right? So the usual choice is to take the Matsubara frequency with a band around it, which makes sense. You can justify if you go to higher order, you can absorb contributions in logs and so on and so forth. So there's some sort of hand waving, sort of formal arguments why you should choose this kind of band. So this is a traditional band for the usual thermal QCD. In the present case, we have 3 mass scales. We have temperature, we have mass, and we have EB. Same thing as we would have if we had a chemical potential, right, instead of EB. So in the literature, one will find several different assumptions for the form of the running. So we'll consider some of them, right? So as I just said, we'll show for a few representative choices and discuss the implications for observables and see if we can kind of choose the best one or something in this direction. Although that should be really something tested on the lattice. So the lattice can bring the answer somehow, hopefully, right? So we have a preference, of course, right? But we'll show all of them. And I guess the preference will be kind of obvious. Yeah, 5? Okay, I have to speed up. Okay, so we have fixed one, trivial, no running. We have this running here, which appeared and became famous because the motivation was to try to provide an understanding for inverse magnetic catalysis. If you know what it is, great. If you don't bother. You have the same one as this one, but here you have a fixed lambda bar, and here you have a lambda, which is 2 pi t, right? And you have QCD running with the usual thermal choice, like this, where you basically ignore B in the running scale. And then last but not least, really not least, you have this one, which is an extension of what is done in medium field theory. So again, of course, what we prefer is this one, but still, you're going to show everybody. So if you show results for the running coupling, you can see alpha as a function of t, alpha as a function of EB, and you see that cases 2 and 3 display an unphysical behavior with increasing B. I'll go very quickly here, otherwise I won't show anything. So these guys are going up, right, with EB. So you see a bunch of plots going up with EB, and this makes me nervous, right? Because then it's incompatible with asymptotic freedom. It renders perturbative calculations meaningless with high B and so on. So I got nervous with this. And if you look at cases 4 and 5, it exhibits the usual QCD behavior. So it goes down and it's all fine. There's a quantitative difference because in case 5, B contributes also to the running of the scale. You can do the same thing with the mass and same kind of arguments here. I'm going to speed up and just skip this mass running, but same kind of thing that you observe. And then you can compute the pressure, right? So here you have the free, you have the exchange contribution, you have the ratio, which is a kind of a measure of how well you're doing in perturbation theory. And you have the full strange contribution, which is a more affected one by anything, right? So, and you have for very, very ridiculously high magnetic fields here, as you can see here, it's like 800 GeV squared. It's really ridiculously high. But just to see how different prescriptions of the running go. So these guys are just shoot up, right? So perturbation theory makes no sense in that regime. And these guys are sort of, well, one is fixed alpha, and the other 2 runnings are doing fine. This is the running we actually prefer, right? And here you also can see this guy for different P. So it's for 9 GeV squared, and this is for 50 GeV squared. And you see one kind of behavior these 2 cases have here, right, for very large B, whereas all the other cases show a much more well-behaved way of approaching zero. Not zero, but smaller temperatures. Okay, so these are already said. And then the full pressure with bands is this. So you have increasing, so the band is increasing and decreasing the renormalization scale by a factor of 2. So this defines the bands. This guy is essentially blowing up here. Case 2 has no bands by construction since this lambda is fixed. And so you can compare the 2 cases. And again, you see that this guy is essentially blowing up. So then finally, I can show some results. These were original results already because we didn't have bands. We didn't have much more control of the pressure, and we didn't have running or anything like this. But now we can show new observables, and then we can show results for the Carroll condensate here. So again, the different cases are here. Lattice data is here. And it's sort of in the same ballpark. If you look at the small bands here, this guy is essentially blowing up again, right, in this region. And these guys are kind of nicely behaved in this region here, even in this range of temperatures, right? So this, again, this is a not right place to compare. But what is interesting for us and kind of stimulating is the fact that it's in the same ballpark. So it's not doing badly, right? Okay, so we can show very quickly results for the strange quark number susceptibility here. And again, as a function of temperature here, and for different magnetic fields, 4, 9, and this is for the old results by Androdi, 3.25. And so you see that they're in the same ballpark, but we cannot still see if it has the same qualitative nature as it goes to very high B fields, right? So I have data from these two different groups here. Qualitative behavior for different running choices, they change significantly. And lattice data is still far from this region. So I'm pretty short on time. So I'll just move to my final remarks very quickly with some basic messages to leave you. So first, this magnetic thermal PQCD with physical quark masses, that's what we do, indicates that these loop corrections are subdominant in the pressure, in the pressure for large B. So next leading order term is comparatively very small for finite temperature. So the window of applicability is still narrow, but these results can be obtained from clean first principle calculation. That's the theory in that limit that can be systematically improved and controlled. So that's the most important point. That's something under control. It's a clean calculation, and you can compare in a given region. So no hidden stuff, nothing like this. So the convergence of the perturbative series for the pressure using the most commonly adopted choices for the running show the following. So cases 2 and 3 show convergence problems. So I think they have no sense for large B. And cases 4 and 5 pass this criterion, case 5 being the most well-behaved, in my opinion. So of course, it would be great to have lattice results to help clarify this issue. And so the results for the chiral condensate and the strange quark number susceptibility, which we compared to recent lattice QCD data, away from the chiral transition. So for very large, not so large as we wanted, but large T as compared to the critical temperature, they're still out of the region of validity, but PQCD seems to be in the same ballpark, which is encouraging. Again, we'd like to have lattice results at even higher B and T. So I didn't show here, but I have results already with these collaborators that show that for huge values of B, one can extract analytic results, which is not possible at finite T, in the case of cold magnetic PQCD. And then we can see the infrared logs and so on. So this might be relevant for magnetar microphysics. So with that, I thank you for your attention. Sorry for rushing out.
Eduardo, thank you for the nice talk. QCD is very beautiful. But I have a simple question. Maybe I missed what you said. When you start to increase so much the magnetic field, does the running coupling constant should also run with B?
It's running.
Not?
Yeah,
it's running. I missed
the different runnings give different results, and some of them are very unphysical, depending on how you choose the scale. So you can choose the usual running, or you can try to mimic some behavior and then choose some different kind of running just to explain inverse magnetic catalysis and so on. Yeah. So there are many different proposals. 4 of them are very representative. So we showed 4 of them. Mm-hmm. There's another one here. Yeah.
Okay. Now it's okay.
That's okay.
If B is very large, suppose it's incredibly large, so we can throw away the quark contribution?
No.
Never?
No.
In the running of the alpha?
No.
No?
No. It enters, yeah.
It's a short one. I just wanted to see, does the magnetic field helps or in the convergence of integrals, or
it helps in the way you build, the loops. Yeah. In the convergence of those particular integrals we have to solve in the end, yes, because you have this E over something with the magnetic field minus something of
I
magnetic
saw
field
that
killing.
the B appears in the denominator. So
Yeah,
it
but
seems that
it's also, it's a composition. It's not trivial to see, but it's a composition that is regulating also the UV limit. So there's no problem
so
with
in
the
the
UV
end it
limit.
helps.
Yeah. The second question related to that would be adding the new terms, higher order terms, and seeing if the convergence gets better. Because the exchange is shrinking, at least in the chiral limit. The chiral limit, the exchange is 0, right? Which is different from the case with non-zero, with 0B, very different.
Thank you. Just an experimental question. Maybe
Yeah,
I missed
sure.
your early motivation.
Sure. No, I didn't show any, sorry. I just mentioned briefly, yeah.
No, at some point, of course, all of this, people have different ideas or judgment about what's good and not good. But my point is, what type of observable, what type of system you would like to see measured, and what type of observables?
It's being measured in heavy ion collisions. So since RIC, so non-central heavy ion collisions will make a very large magnetic field, right? Because of the currents.
Okay.
So I have the largest magnetic fields ever produced in the universe are in heavy ion collisions.
Okay.
Right. So 10 to the 19th Gauss.
All right.
This is huge.
Yeah.
Right. But they don't last very much. Or we don't know if they can last very much. We don't know if they can last very much. That depends on how you magnetize the matter that is formed, that the quark gluon plasma that is formed.
Yeah, but this is where I have a problem. You see,
Sure.
So the issue of saying already you have a quark gluon plasma.
Yep.
And what does it mean? And then you are coupling it to a large magnetic field that exists there.
Yeah.
So my problem is really that you don't have any direct access to the conditions through the observables. And that makes it a little bit hard in the sense that, what should I measure and how could I have a direct evidence of something?
Yes.
And I would have liked to see perhaps, lattice is great. It's a way to actually explore all of this. But at the same time, it would be nice to show some experimental.
No, absolutely. I didn't put that because I didn't have time. I have in my laptop, I can show you, but I didn't put it because of lack of time.
One naive question. So in your case, the magnetic field changes with time, right? It's a time-dependent magnetic
Not
field.
here.
Not here. Okay.
Not here. In the collisions, yes.
Okay. So in your calculation, it's independent of time.
Fixed.
It's constant.
No time here. It's
also
equilibrium.
it doesn't depend on the spatial, let's say,
No. It's uniform
constant.
magnetic field.
So
It's
it has
already
fixed
hard
direction.
enough. Yes.
So then do you imagine if you use, I imagine you use the covariant perturbation theory, right? Not the light front perturbation theory.
Light front. I don't know.
So do you imagine that there's any less advantage because this magnetic field defines a special direction?
Yes.
Whether there's any advantage performing light front perturbation theory instead of covariant
Could be.
theory?
Never thought about that before, but I mean, I'll be happy to hear from you on that. Yeah.
Okay.
Could
Thanks.
be.
Maybe a naive question. It's just to,
This
yeah,
previous?
yeah. I mean, I don't know. I see dots totally out of the curves, and I don't.
Yeah. But I
understand
mean,
exactly. So this is
yes.
this is out.
So these are
totally.
the bands. I'd like to compare it here, right?
Yeah.
I cannot show because the pointer doesn't go there, right? So this one, I'd like to compare it here, right? But the lattice is still here. So it's going in this region here, and we have the bands that go in the same region. What is not obvious is that I could have computed this and obtained something which is like 100 times larger or 100 times smaller, and it's not. It's kind of in the same ballpark.
Okay, so the point is that you are in the same scale somehow.
Exactly.
Okay.
Exactly.
Now I got it.
Magnetic fields produced in heavy ion collisions are not uniform. They
Yeah.
vary a lot. Is this non-uniformity taken into account in any kind of study?
In some simulations and so on. But if you want to do this here, it's going to be awful complicated, right? But so what you can argue, maybe that's directly related to his question, is that if you have a plasma that is large enough formed there, and you magnetize this plasma for long enough time, then it could be approximately uniform in a given region, and that should be maybe enough to compute things, right? Otherwise, you have to do things a lot more complicated. So what we're trying to answer here is a way simpler question, which is how QCD behaves under very strong magnetic fields. So the way I can answer this perturbatively in a very controlled fashion is if I have, if I have this situation here. If I have this, my calculation is under control. It's clean. That's my point. It's clean. Is it directly compared to experiments yet? No. Yeah. There is some arguments from some old, very relevant papers in this direction that will have very large magnetic fields. Actually, from the previous time, from the electroweak time, generated there and remained until the QCD epoch, right? And then they could play a role. That's again thermal field theory. And differently from heavy ions, the universe is large at this time, humongous, and very slow. It's 19 orders of magnitude slower and larger than heavy ion collisions. So, but we don't know if we have these fields. In heavy ion collisions, we know. So we don't know if they magnetize the matter for long enough, but we know we generate them. So that's the motivation in terms of, and you're doing the experiment, right? So you can measure whatever you want. In the early universe, it's kind of harder, right? You have to find some relic, right? So it's kind of hard.
Okay, well, let's thank all the speakers for this morning.
Yeah.
And before anybody leaves, if you are going to the banquet tonight, please pick up your armbands in the coffee area. What's that? Yeah. Oh, there we go. Okay. One of these works, but I don't know which one.
I hope. I hope so. Yeah. It's a different point of view.
Okay, welcome to the second half of the morning session. The first talk for this session is going to be by Nelson Braga, and he's going to talk about effective models for heavy mesons in a plasma inspired by gauge gravity duality.
Thank you. I would like to thank the organizers for the invitation to present this talk. First, I would like to give you a general idea about what is the kind of study that we have been doing, what is the motivation. The main motivation is to understand the quark-gluon plasma using heavy mesons to this study. As you know, we do not see the quark-gluon plasma. We cannot observe it directly. We just get information about the quark-gluon plasma looking at the particles that reach the detectors after the hadronization process. So it's very interesting to look at particles that could give us more information about what happened. How was the plasma? What was the temperature? Was there the presence of magnetic fields, angular momentum, finite density effects? So the motivation is this one, to look at heavy ion collisions that form a plasma, quark-gluon plasma, using heavy mesons, charmonium and bothmonium. They provide information about the plasma because when the plasma is formed, these particles are produced. And the light flavors, they dissociate to form the plasma. And at least part of the heavy quarkonium states, like we call the heavy meson, charmonium, and bothmonium, the quarkonium states, they survive this melting, this dissociation process up to some temperatures, densities, magnetic fields, angular momentums. And so they undergo a partial dissociation, we can call like this. They can partially dissociate. So the fraction of quarkonium states that we observe after a heavy ion collision can serve as an indicator that you can use to look at the plasma and to find out information about the properties of the plasma, like these ones here, particularly the dependence on the, if you know the dependence of the dissociation process of quarkonium states on the temperature, how the dissociation increases with the increase in temperature, with the presence of magnetic fields, with density. And I put this in red because angular momentum effects are something that only recently have been studied. There is a lot of study about the effect of magnetic fields. We had this very nice talk by Eduardo before coffee break. And there is something I would like to comment at this point. In the same way that studying effect of magnetic fields is something non-trivial, and as a first approximation, people normally think of a medium with a homogeneous magnetic field. A similar thing happens when you study rotation effects. If you have a plasma, it's like a pizza because of Lorentz contraction, something like that. And the rotation is not uniform, okay? But to get some initial information, what we did in the first work about this was to look at a cylindrical shell, a region that has the same speed. We also have a work that consider different slices and inhomogeneity of the plasma, but we use a similar argument that is used for magnetic fields, that is to first consider uniform rotation, to understand just what is the effect of rotation. All these things we do using holographic models. What are holographic models? First of all, it's important to make it clear that they are models. They are phenomenological models. They are not a fundamental theory or anything like this. They are inspired in string theory, in particular ADS-CFT correspondence, but they are not really, they are just models. We don't have a proof of the equivalence like Maldacena had for the ADS-CFT. ADS-CFT is just an equivalence between string theory in 10 dimensions and a gauge theory in 4 dimensions. That is the boundary of the theory. In summary, Maldacena found an exact equivalence between a sort of string theory and a special kind of gauge theory in 4 dimensions. That's great because, okay, there is a relation between string theory and a gauge theory in 4 dimensions, but this gauge theory is very different from quantum chromodynamics in many senses. It's supersymmetric, it's conformal, and it's obvious that after Maldacena work, everybody wanted to find a different correspondence that, okay, this is quantum chromodynamics, but this is a very, very, very complicated job, but something that is much more feasible that we can work in is to use this idea that, okay, Yang-Mills theories are related to some kind of string theory that actually in some of the energy regimes that we look at are not exactly string theory, but just supergravity theories. And this fact that there is a 10-dimensional space, we forget about this because 5 dimensions are related to supersymmetry, and quantum chromodynamics is not supersymmetric. So basically, we build up models in 5 dimensions, and they are just fields in curved space, just gravity solutions. And the space is anti-de Sitter with some eventual modifications. It's a 5-dimensional space that have one particular dimension where you have a warp factor. If you move in this direction, the metric changes, and the transverse directions are just Minkowski, and the boundary is Minkowski space, so it's a gauge. We want to build up, represent a gauge theory in the boundary that is just Minkowski. And there is the holographic mapping, is a mapping between, for our use in the holographic model, is a mapping between a 5-dimensional theory in a curved space-time and a 4-dimensional gauge theory in flat space. And what we do is try to modify the ADS-CFT correspondence based on the way that, for example, energy is related to the position of the 5-dimensional coordinates and things like this, in order to find models that are close to what we see in quantum chromodynamics. And this is a very, very long story, but soon after Maldacena work, many people, like our group, built models for calculating masses of blue balls and things like this. And the results are quite reasonable. And the models are, at this point, were quite simple also. Okay. But now, I told you I was going to talk about quark-gluon plasma. Quark-gluon plasma is a medium with finite temperature. How do we put finite temperature in this stuff here? Okay, soon after Maldacena proposed the ADS safety correspondence, Witten proposed an extension to finite temperature. In the ADS safety correspondence, you have an ADS space dual to a gauge theory in the vacuum, low temperature. What Witten proposed is that if you do not use pure ADS space, but just an ADS black hole. What is an ADS black hole? It's a black hole that when you go very far from the horizon, it's asymptotically ADS. Okay, and the temperature of the black hole will be the temperature of the gauge theory. And after that, many other people worked with this purpose of looking at a medium like the quark-gluon plasma, adding more ingredients to reproduce what we have in the plasma. For example, it is possible to, and it was done, to reproduce a medium with finite density using a black hole with charge. You make some correspondence between the charge density and the density of the medium. And so it's possible to reproduce not only a medium, a gauge theory in a medium with temperature, but also with density. And magnetic fields also, we can put in the background magnetic fields and reproduce this with magnetic fields. And as I told you, more recently, we have worked, and some other people also in other places, but very recently started working with the modeling, the holographic modeling of a plasma with angular momentum, just using a coordinate transformation that makes the black hole has angular momentum. The situation is simple, that I have a black hole, I assume it's dual to a plasma. I make some coordinate transformations in the transformation in this black hole. And if I look at this new geometry and calculate the angular momentum of the geometry, and we know how to calculate angular momentum for a black hole, you have a finite result. The initial black hole had zero angular momentum, the new one has angular momentum, so we assume that this black hole reproduces a medium that is in rotation. And why do we want to study rotation? Simple. When you have this non-central heavy ion collision, everyone thinks about magnetic fields because, oh, we have charges moving very fast. Okay, but in non-central collisions, you also have a very high angular momentum. So this is an important effect to be studied also, not only magnetic fields, but also angular momentum. Okay, and how does story of holographic models work? I will just give you some short hint about the idea about what we do. We have a model where we have fields that represents the states, or better, the quasi-states, because they are in finite temperature in a medium, of the particles we want to describe. And we put them in this 5-dimensional anti-de Sitter space. 5-dimensional anti-de Sitter space is what appears in ADS CFT correspondence, but we put more. At this point, we become to just build a phenomenological model. We put a background, and there is a long story about this kind of backgrounds that we use in holographic models that started with hard wall models, soft wall models, but we found this was a collaboration with a former student, Luis Fernando and Alfredo Vega from Valparaiso, Chile. We found a kind of background that if we solve the fields that live in this background, we can reproduce masses and decay constants for the mesons. We have some new results. I have some new results with some students now that are better than these ones, but okay, this was a starting point. And so we have this fit of decay constants and masses, and we realized that something that most of the people that build models for reproducing hadrons holographically, they are worried about masses. Okay, I fit the masses, that's great. But we realized that decay constants are very, very important, because when we have 2-point functions of particles, you build up the spectral function, for example. The spectral function at zero temperature is a set of delta functions with a factor in front of it that is the decay constant. So if you have a holographic model that has bad values for the decay constants, your calculations of spectral functions would be very bad. The dissociation process would happen in a temperature that has nothing to do with the real process. Okay, just to give you a flavor about what we do, we have some kind of metrics that represent, for example, this kind of metric is to represent a particle, a medium with a density, finite temperature, density. This is for a presence of magnetic fields. And with this, we get the spectral functions. Spectral functions is something that, in a very simplified way, we can think that is an object that gives you information that if you look in a medium and search for a particle, what is the energy region where you have more probability of finding the particle? If you have just one particle at zero temperature with a mass, it is just a delta peak. Yeah, sure. Yeah. It's not. Yeah, we have to. Yeah, optimize what is for both, and yeah, because the behaviors are a bit different. And one thing that happens is that decay constants, I showed you the table, they decrease with excitation level. Depends on the definition, but with the definition. And all the other holographic models that we had before this one, hard walls, soft walls, Sakai Sugimoto, the 48 model, in all of these models, the decay constants would increase or just be degenerated constant. And we had some work with this bad decay constants, and the spectral functions are terrible. And these ones, they dissociate in temperatures that are completely consistent with what we see. For charmonium, for bothonium, what happens? This blue line is for charmonium, the spectral function at 150 MeV temperature, the second one 300, then 450, 500. So increasing the temperature, the peaks of the spectral function, they get broadened, means that they have a lower height and they are wider. So, no? Sure. No, this 2.22, oh, it's a very interesting question. There is the localization is a thermal mass that is not exactly equal to that mass. Yeah, the mass change also. We also calculate what we call quasi-normal modes. Quasi-normal modes are really the solutions that correspond to the quasi-particles, and they have a complex frequency. And the real part of the complex frequency is the thermal mass, and it varies with the temperature, varies with magnetic field, density. So we didn't make any adjustment, and we just observed, okay, the mass is, you can see in this first plot that the mass is shifted. So this is the effect, thermal effect on the mass, that when we calculate quasi-normal modes is translated in the variation of the real part of the frequency. 2 points. Charm quark, yeah. Not quark mass appears. We interpreted these parameters as being related to quark mass and to string tension, things like this. But this value was the mass. For bothonium, that's why we study more presently bothonium than charmonium, because it dissociates at higher temperatures, so you can see more states of bothonium. That is something I should remark here, because we are looking at just one particle states. If you decide to look at the spectral function at much higher energies, you can form two particle states, and this gets a mess. Okay, so I just look at one particle states. If you have two particles, you can have some internal energy, and then it gets completely different. Okay, just one particle states. And this is just a sample of variation of the spectrum of charmonium at 200 MeV temperature for different densities, 0 MeV, 100 MeV, 200. And we see that the increase in the density of the medium also increases the dissociation effect on the particles. Here's a similar plot for bothonium, and what happens is that this blue peak is the case with zero density, and then if you increase the density, the peak will get slower, so the dissociation effect would be greater than, okay. And similar thing for the effect of magnetic fields. Magnetic fields also increase the dissociation effect. The presence of magnetic field enhances the dissociation process. So this relation between this dissociation process, the dependence on dissociation process on temperature, magnetic field, density, is something that can be used to look at the result that you have in a heavy ion collision and try using not only this information, but also some other general information about the particles produced in the collision to reconstruct the plasma, okay? I have 5 minutes, okay. Here also effect of magnetic fields on, and all these results we get, especially the dependence on temperature, is consistent with the results we find from other approaches. Dissociation effect with density and magnetic field is something that is not easy to compare or to find results from other approaches. Okay. Now I want to show you what we do to describe a plasma in rotation. We use, as I said, a simple model where we take a region of the plasma that has the same speed. So is at the same radius with respect to the rotational axis, just to simplify the situation. And then we make a transformation. We take the cylindrical space and make a transformation in the cylinder. We use a black hole with cylindrical symmetry, and then make a coordinate transformation. With this coordinate transformation, we build up a black hole that has angular momentum, and assume that this is due to plasma that is rotating like we expect to find in non-central heavy ion collision, where this plasma has a high angular momentum indeed. Okay, and we analyzed what happens with the transition confinement, the confinement transition temperature when the plasma is rotating, and found both for two kinds of very simple models, hardwall, softwall, that the critical temperature decreases with the rotational speed. And this is something that's somehow trivial, I would say, because there is a notion of local temperature for accelerated observers or for curved space. It's due to Tolman and Ehrenfest. And if you use this notion of local temperature, you'll see that rotation makes a local observer to see a different temperature. So we realized that after calculating this, that there is an explanation that is consistent to what we have in the analysis of temperatures in general relativity. Okay. Oh, I had some slides about the configuration entropy. I will not show you because I prefer to go to this. Okay. We have a very, very recent article. We placed it in the archive yesterday. I think it will appear tomorrow night with a graduate student, PhD student, Ian Ferreira, where we used this model of the plasma in rotation and use this metric of the black hole that is rotating and put the background that represents bottomonium. That is a kind of background I show you with a hyperbolic tangent, a phenomenological model for the bottomonium. And then Giancarlo Ferreira was calculating what happens with the spectral function of bottomonium if you have bottomonium in a medium, in a plasma, and the plasma is rotating. And these plots are some of the results he obtained in this article that will appear, I think, tomorrow. If you have bottomonium at 200 MeV, you have these two peaks, first peak, second peak, first state, ground state, first excited state. And if you put a rotation with a velocity that is 0.4, taking c equal to 1, you have this decrease in the second peak. If you increase the velocity 0.6 of the speed of light, if you have this much larger decrease, and then at 0.8, you have the complete disappearance, the total dissociation of the bottomonium first excited state in the medium. So rotation increases the dissociation process. And this is an important fact, because if you are looking at the spectrum, at bottomonium that appears in the detectors to understand what happened with the plasma, if the plasma was rotating, this fact has to be taken into account, the corrections associated with rotation. But as I told you, this is a simple study because we took just a cylinder of plasma rotating. But if you know the temperature increases the dissociation effect, if the medium is not uniform, okay, it doesn't matter. Dissociation will increase with rotation, but the details depend on more models. But okay, I will stop here and thank you very much for the invitation, for the audience.
Thank you very much. Are there any questions for Nelson?
Very naive question. Thank you for the talk. Very inspiring. Landau levels, how it appears in orography?
Interesting question. Landau levels. Yeah, with rotation. I don't know how to answer this now, but it's an interesting point. I think. Thank you.
Hi, Professor.
Hi.
Nice talk. I have a question. Do you show the results to the bottomonium with the rotational effects and magnetic effects? There is a way to put these two effects together, or?
We are thinking about this. Yeah, there are some, non-trivial points. But it's a very important point. You want to compare these two effects, but the difficulty is that, as I told you, we just used a cylinder because this way you have a region where all the points have the same speed. Okay, if you want to put a region that is not just a shell, you have to superimpose different black holes and so. And looking at the magnetic fields, the difficulty that we have been discussing about is what would be the direction, because if you have this cylinder,
where would be the magnetic field located? What is the direction? Okay, but we are thinking about this, and the comparing these two effects would be nice, because these two quantities must have some kind of relation, because the angular momentum depends on the velocities of the ions, and the magnetic dipole. So the magnetic field intensity is also real. So they're probably related, but we have some technical difficulties because the way that we reproduce rotation is using this cylinder, and then the way to put at the same time magnetic field we are a bit difficult to doing this, but we want to do this. Thank you.
So just a quick comment and a question. Thank you, Nelson, for the talk. And so the first one is that at the very beginning, when people were studying magnetic fields and heavy ion collisions, they were directly interested in the angular momentum too, because these two guys are directly related, right? So, but they got attracted to the magnetic fields because they wanted to separate charge and to see the chiромagnetic effect. But from the very beginning, this thing was there, and people got distracted by the magnetic field, so to speak. But I think they should definitely be related. The other thing is that do you know how the critical temperature changes? I mean, quantitatively, with respect to the frequency. Do you have numbers that could be compared to heavy ion experiments, for instance? I mean, the kind of angular
temperature
frequency and TC and so on.
Yeah, we have a very simple.
So what? How many
It's
percent?
just a factor of 1 over gamma. Up here. Yeah. Yes, in this simplified models is just a factor of 1 over gamma.
Yeah, but I mean, in terms of what would be the units? If I put units like MEV for temperature and 1 over millisecond or second for frequency and so
temperature
on.
of the plasma without rotation times the factor 1 over gamma if it is rotating with a uniform velocity. The real plasma is not like this. You have a region. So
no, that's okay. I mean, I don't
a
care.
very interesting thing happens. We have another article. It's with a postdoc, Otávio. You may find a situation in which you have a plasma that is spread over a region. It's rotating. The central points have lower velocity. The external points have higher velocity. So you can have an inhomogeneous situation, medium, where for radius larger than some critical radius, you will have a plasma, the confined phase. Inside, you will have a confined phase. There is an article by Maxime Chernobyl.
Yeah, Maxime Chernobyl has been
about
studying
this,
rotations for a long time.
He wrote to us and told about his article. So he wrote a second article using his remark about this. Yeah, we have this because if you have a plasma, a real plasma rotating, you have regions that have different radius, so they rotate with different speeds. And you may find the situation of non-homogeneity of the medium. Outside you have plasma, inside you have hadronic matter. In this work by Maxime Chernobyl, he analyzes this not using holography, but different things. It's a very nice paper by Maxime. Thank you.
Thank you. I think we need to move on to the next talk then. Thank you very much, Nelson. And the next talk is by Adamu Hisfu, and he's going to talk about exotic baryons and hot neutron stars.
Okay.
Thanks for the opportunity. This is my first time on this platform, and it appears I haven't seen so much of astrophysical stuff being presented. Anyway, I think I'll not be out of context anyway. So we studied exotic barons in a neutron star, considering its evolution. It's here? Okay. And again? Okay. So we use a relativistic model within the mean field approximation with density-dependent couplings for this study. And then the models were adjusted by the DD-ME2, that is density-dependent meson-nucleon coupling, to adjust the models. These were determined through fitting to bulk nuclear properties. And then we did our study at a fixed entropy, calculating the nuclear equation of state, looking at the particle distribution within the star. Then we look at the temperature profile, how the temperature increases with density as the star evolves. And then we look at the sound velocity to see, to test some properties. And then we construct the macroscopic structure of the star as well. The talk will be based on this paper in collaboration with Kawan, Mateus, and then Deborah Menezes. So basically, this is a heavy star that has used its fuel, about to explode. In this case, you have inside the core of the star, inside the core, you have a protoneutron star with a fixed electron density, entropy, surrounded by a heavy higher entropy. So at this stage, the star is trapping neutrinos, getting heated and receiving shocks from the external part to explode. So after it explodes, it depends. If it accretes more mass, it can form a black hole. If it doesn't, if the mass is within a particular threshold, it bounces into a protoneutron star. At this time, after the bounce, it starts losing the neutrinos. The neutrinos start diffusing. The star starts to heat and then getting leptonized. And then the process continues. It gets to a point where the neutrinos, all the neutrinos are gone. The star gets heated, maximally heated. This is the peak point. So it will start to cool down to a cold neutron star. So you get to, the entropy reduces to 0. At this point, it's at catalyzed, and then it will continue cooling by emitting radiations. That is pair of neutrinos, photons, and what have you, to get cooled into a cold neutron star. So basically, so many forces are at play here. You see that at this point, it's in the strong gravitational force, and where it starts emitting neutrinos, we have weak force at play. And then when it's the heating, the thermodynamic effect, you would have a strong force, and then you have an electrodynamic effect, and then strong force at play. And then when the composition of the star changes, you have a weak interaction at play with a strong interaction taking place. So, 、 So this is a cross-section of a neutron star. We have an outer crust, inner crust. The same way we have an outer core that will be around here, and then inner core. Our interest will be from the outer core to the inner core. The outer core, it begins at approximately 0.5, the saturation density, neutron saturation density. And then the inner core will start approximately twice the saturation density. So here we know that there are neutrons, there are protons, there are electrons, but in the inner core, no one really knows what is there. So people put kaons to see the characteristics of the star, put free quarks or exotic barons to see the characteristics of the star. And that is what we would put, we will introduce exotic barons to see how it evolves with these particles. So, okay, this is the model. We use a relativistic model. So we have hadrons, we introduce hadrons. Here you have all the hadron octets. And then we add delta resonances. And then we have mesons that mediates the interaction between the barons. And then we have free leptons too as well. So this is how we use the mean field approximation. So this meson fields, we have already taken the mean field. So this is a vector isoscalar meson. This is also a vector isoscalar meson with hidden strangeness. And this is a vector isovector meson as well. And then the sigma is a scalar meson. Whilst these fields are it's just like the Dirac equation. So these fields are the Byron fields. It contains all the octets. Again. Okay. So the delta isobars have a different characteristics because their spin has a additional projection. So they are described by the Larita-Schwinger type model, Lagrangian. But in the mean field approximation, it is determined that this Lagrangian has similar equations of motions like the spin half models, but it is proper to emphasize that they have a different description. And these are the meson field. I've already taken the mean field, and so I have dropped the terms that depends on derivatives and kept only the linear terms. Then these are the free fields, the lepton fields. They are represented by this Lagrangian. I have to press with pause. Okay. So these are sorry, okay. So the model is adjusted by this coupling. The variables we are seeing, the B, A, B, C, and D, they are fitted through bulk nuclear properties. Okay. It's not moving if I press. Okay, so let's move on. have few time left. So we have the chemical potentials depending on the meson fields, and then the rearrangement term. These rearrangement terms come into play because of thermodynamic consistency and then energy momentum conservation. Okay. So what the most important parameters we are interested in are the energy density, the energy densities and the pressure that is that I've put in blue. Here, we realize that we do not know the fields. What we don't know here is the fields. We don't know the meson fields. So we calculate we determine the meson fields. Oh. Getting back. Okay. So we calculate this equation of motion. We determine the equation of motion and solve it together with the baryon density and then the scalar baryon density to determine the meson fields. But the couplings, we know them. They are already determined. Okay. So this is the values for the couplings we used. This was determined through group theory using symmetry arguments. So we adjust the model using this parameter. This is the DDMU2 parameterization. So this is the effective masses required, and then the total energy density and the pressure. The pressure has a correction from the rearrangement term. And then our calculation will be based on this relation here. We'll fix the entropy density, and then we calculate the temperature and other properties of the star. So the most important constraints are that we do our calculations at a beta equilibrium, using beta equilibrium. Make sure there's charge neutrality. We make sure lepton numbers are conserved, and then baryon numbers are conserved. The beta equilibrium process is basically, it follows the direct recap processes because the neutron fluid is quite unstable. So all these relations, two relations, have to be satisfied simultaneously to ensure that we have a stable system. So let's see the particle abundances of the model. We calculate the particle abundance. We realize that from here to here we have a higher lepton and then proton densities. And then here it starts decreasing. So you see, if you have higher neutrino, if the star is trapping neutrinos, higher neutrinos, it affects the proton and then the lepton densities, and then the appearance of the particles too as well, where the exotic particles appear. We see that here we have the resonances, the delta resonances appearing far before the delta particle, the strange particle here. And then when the neutrinos start diffusing, we see that the particles appear at lower densities. Almost all the particles at this part has appeared even before twice the saturation density. And then another thing, when we compare the proton number density and then the neutron number density, we see that this asymmetry increases from when the star starts trapping the neutrinos and when it the neutrinos starts diffusing. Okay. One. So here is a neutrino transparent. When the star has already the neutrinos, there are no neutrinos anymore trapped. And then here the star is heated, it's maximally heated, and starts to emit radiation to cool down. And here we have a cold neutron star. We see the particle distribution. You realize that when the when the star is hot, the particles shift more towards low density. And then when it is cold, they move more towards the middle of the star, that is in the core. So basically, that is what I've described. Move on. Here is the equation of state. The equation of state, we realize that when we add more degrees of freedom to the system, the pressure decreases. That is, the equation of state becomes more soft. And then as the star cools down, at this part, we see it clearly that the pressure inside it becomes higher. So increasing entropy affects the stiffness or the softness of the equation of state. This is the temperature profile. So here is when the star is trapping neutrinos, getting heated, and then when it bounces, that is the core bounce. After it starts, when it starts diffusing neutrinos. And then here is when there are no neutrinos at all in the star. That is, it gets maximally heated. So this is the first stage, what you see, second stage, and then the third stage before it catalyzes to a cold neutron star. So we determine the nature of the star, the mass radius diagram, using this relation. So using this relation, we have already assumed a spherically symmetric fluid, and then we determine the mass radius diagram here. Because we put in some observable pulses here. This is the pulsar determined by NISA. This also true, and this is a heavy pulsar also determined. We realize that the radius, which is the yellow dot with the error bars, are outside our range, but we have the mass ranges are right. This is because the star is hot at this point. So here too, we see that when the star gets cold, we satisfy these two, all the observed pulses. Our results satisfy all the observed pulses. So we determine the sound velocity. What is important here to show is that when the star gets cold, we see that the particles are in layers. So we see the shocks directly when we calculate the sound velocity. So here too, there are some few conditions that have to be satisfied. The gray line here is the exactly conformal line. Below it is when you have particles that observe conformal symmetry, that is quarks, free quarks. And then because of causality, we shouldn't have speed of sound greater than 1. And then for thermodynamic stability, speed of sound should always be greater than 0. So summary, we observe that entropy density affects the particle distribution. The higher entropies, we see that the particles shift towards the lower densities, and that softens the equation of state. And then when new particles are introduced, that is, new degrees of freedoms are added to the system, the temperature reduces, and then the speed of sound also the speed of sound also reduces, as we saw. And then increasing entropy leads to an increase in the radius, temperature, sound velocity. In the neutrino transparent region, the stellarity is greater, as I showed in the mass radius diagram. The future projection is that we study how dark matter affects such evolution of stars and so forth. Acknowledgement. Thank you.
We have time for one question.
As an experimentalist, I always wonder what I could observe. Would I see something in the neutrino spectrum or whatever, which confirms or deconfirms your theory?
In what sense? I don't really get it.
Yeah, I don't know. Are there any observables that can prove your theory or not?
Well, it is the pulses I showed, but you realize that when the star, actually those pulses from our results, it is when the star is cold. When the star is cold. So when the star is really hot, we don't really know if it can be observed. But from the results, when the observed pulses fall within the range of the cold. When the neutrinos have already gone off.
Thank you very much. Oh, we need this, the mic. Adamo, you want the mic still?
Oh.
Okay, the next talk is going to be by Filippo Fornetti, and he's going to talk about the EMC effect within the light front Hamiltonian dynamics for few nucleon bound systems.
Good morning. Good morning, everybody. First of all, I want to thank the organizer. So this talk is based on those papers, and I show the result of the recent work for the helium-4. So the goal of this work is to extend the approach applied for helium-3 to any nuclei and calculate the MC ratio for helium-4 and tritium. Since helium-4 is a strongly bound system, this could provide a challenging test to our approach. And we also compare the results for helium-3, helium-4, and tritium obtained by using different modern two-body and three-body interactions. We also compare the results by using different choice of the free nuclear structure function parameterization. So the EMC effect was discovered almost 40 years ago by the European Muon collaboration in deep massive scattering processes of nuclei. And they measured the ratio of the nuclear structure function over the structure function of the deuteron. They expected the ratio was 1 up to the duration to Fermi motion, but the result, as we can see, was that the ratio was not equal to 1. For first naive model, pattern model interpretation was that the valence quarks in the bound nucleon are in average slower than in the free nucleon. So we can observe three regions of the EMC effect. The first one is the so-called shadowing region, and now is basically understood because of coherence effect. The virtual photon interacts with parton belonging to different nucleons. Then we have the properly EMC region, where the EMC ratio is less than 1. And we have mainly the work, the valence quarks are involved. And then we have the Fermi motion region. So we see that the EMC effect is not dependent on the Q square. We see weakly dependence on A, and we also see that it scales with the density and with the short range correlations. So we can relate the effect to both global and local properties. So we can, it's possible to explain the effect also by using exotic explanation. By exotic, I mean under beyond the conventional nuclear physics. So imagine that the quarks in the nuclei form bags with different numbers of valence quarks. So the situation now is basically not understood. We need to know the reaction mechanism of active processes of nuclei. So we have a non-relativistic calculation for the EMC effect, and we have a qualitative agreement, but because the non-relativistic nature of the calculation, we have no fulfillment of both particle and momentum samples. So they are not under control, this calculation. So our approach is aimed to include only the nucleonic degrees of freedom through conventional nuclear physics, but in a Poincare covariant approach. So we can fulfill both particle and momentum samples. So I want to remark that because of the magnitude of the EMC effect, it's so small, also small correction due to relativistic effects could be significant if you want to study exotic effect, such as the contribution of the Partonics degrees of freedom. So the standard model of few nucleon systems with nucleon and meson degrees of freedom within a non-relativistic framework has achieved the high sophistication, but we need the Poincare covariance for nucleons with large momenta, and we should carefully treat the boost of the initial and final nuclear states of the elastic process. So we need to use a relativistic treatment, and our framework is the light-form relativistic Hamiltonian dynamics with the Lagrange-Thomas construction of the Poincare generators for interacting theory. So in our framework, we can address both Poincare covariance and locality. So the generators fulfill the commutation rules also for interacting theory, and we can also fulfill the macroscopic locality. So when a system, the nuclear system is separated into disjoint subsystems by a sufficiently space-like separation, we can treat the subsystems as independent systems. But that requires a careful choice of the intrinsic relative coordinates. So we choose the front form Hamiltonian dynamics because there's several advantages, in particular for the deep gymnastics processes. So we have the 7 kinematical generators. The subgroups of structure of the light form boost allow us trivial separation of the intrinsic motion from the global motion, as in the non-relativistic case. And we have a meaningful Fock expansion, so we can fix the degrees of freedoms of our problem. We have no square root in the dynamical operator, and the infinite momentum frame description of the deep elastic scattering processes is included. So Lagrange-Thomas proposed an explicit construction of the 10 Poincare generators in the presence of in the interaction, and the green gradient of this construction is the mass operator. So only the mass operator contains the interaction, and it generates the dependence of the three dynamical generators upon the interactions. And also the eigenvalue problem of the squared of the mass operator is formally equivalent to Schrödinger equation. And the mass operator must commute with all the kinematical generators and with the non-interacting angular momentum, as in the non-relativistic case. So for a nuclear system, we can write the mass operator as the sum of the free mass operator plus the terms with the 2 and 3 body forces operator, where the free mass of the system is written in terms of the intrinsic momenta. And we can assume that the mass operator is equal to the non-relativistic one. So we can use a non-relativistic framework, so non-relativistic potentials, but in a Poincare covariant framework. Oh, for a correct description of the structure function, it is crucial to distinguish between different frames. We have the laboratory frame, we have the rest frame of the nucleus. Then we have the intrinsic life form frame of the whole system. And then we have the intrinsic life form frame of the cluster, composed by the nucleon interacting with the virtual photon and the spectator system, composed by A-1 nucleons. So since we use an impulse approximation, we have to define the light front spectral function, so the probability to find a particle with a given light front momenta when the rest of the frame has energy epsilon with a polarization S. The spectral function is written in terms of the overlap between the tensor product of the plane wave of the interacting particle and the state of the spectator system between the wave function of the nucleus A. That's an eigenstate of the non-relativistic mass operator. So the two states are in the two different reference frame. And so the spectral function will contain the determinant of the Jacobian of the transformation between the intrinsic frame of the cluster and the intrinsic frame of the whole system. Then we can also express the light form overlap in terms of the Eastern form 1 using Mellow's rotations, and then we can approximate the Eastern form overlap into a non-relativistic one thanks to the Brancham-Thomas construction. So in our approach, the hadronic tensor is found to be written in terms of the light front spectral function and the hadronic tensor of the bound nucleon. We can see that in Bjorken limit, the nuclear structure function can be obtained from the hadronic tensor. So the nuclear structure function is written in terms of the spectral function and the free nuclear structure function. But we can see that in the Bjorken limit, we can exchange the order of the integration. So we can use a more simple object instead of the light front spectral function, because we integrate on over the channels of the spectral function. So we use the light-cone momentum distribution, and the nuclear structure function is written so in terms of the free nucleon structure functions and this object, the light-cone momentum distribution. The light-cone momentum distribution is expressed in terms of the squared nuclear wave function. So and we use the non-relativistic one thanks to the Brancham-Thomas construction, and the determinant of the Jacobian matrix that contain the effect of the light front boost through the references frame. To calculate the MC ratio, we need a non-relativistic wave function, and we have to choose a parameterization of the three nucleon structure functions. So we can choose a parameterization of the proton structure function, and then we choose a parameterization of the ratio of the neutron structure function over the proton one, because the neutron one could be only started by nuclear data. And we use a parameterization extracted by marathon data through the super ratio. And for the light-cone momentum distribution, we use three different potentials. We use the argon-Bouettin two-body interaction with the Urbana-9 three-body interaction, and then we use two versions of the Norfolk chiral potentials. So since our approach fulfills macro-locality and Poincare covariance, the light-cone momentum distribution must satisfy the baryon number sum rules and the momentum sum rules. So these are the results for the light-cone momentum distribution calculated for helium-4. The distribution in 0.25 is the light-cone momentum distribution for helium-4. And the one picked in 0.5 is the distribution for the deuteron. and we check the momentum cell rules with accuracy of 1 per thousand. We see that the tails of the distributions are generated by the short-range correlations induced by the potentials. And we see also that the tails of the distribution calculated by the Argonne potential is larger than the one obtained by the Norfolk potentials, but because we have the ratio on the EMC effect, this difference will partially cancel out when we calculate the EMC ratio. This I think because they have to fulfill the momentum cell rules and the barren number sum rules. So the deuteron is speaking 0.5. It would be those are the results, the published results for helium-3. We have the red line, the solid line is the calculation done by Argonne potential with the urbanine three-body interaction, and the dashed one is with only Argonne-Vuitton potential, and we see a small but solid effect comparable with the experimental data. The experimental data from an experiment of the Jefferson lab, but reanalyzed. And then these are the results for the helium-4, and in this plot we have the calculation with all the three potentials. When analogous results we obtain also for helium-3 and tritium for the comparison between the potentials. And we see that the difference within the calculation from different potentials are of the same order for all nuclei and are smaller than the difference between data and theoretical prediction. So we don't have a strong dependence on the choice of the nuclear potential. And then we have in this plot, we have the MC ratio for helium-4 calculated by Argonne-Vuitton with the spin-Moon collaboration parameterization of the proton structure function in a solid line, and the dashed line, the CJ15 with target mass correction parameterization of the proton structure function. And we see that in the probably MC region, the dependence on the ratio as well as the dependence on the free proton structure function is largely under control. So in conclusions, the results increase the confidence in our left front approach, which includes only the nucleonic degrees of freedom. The difference between the ratio generated by different potentials is smaller than the EMC effect itself, so we can say that there is no strong dependence. And the deviation of the our calculation from the experimental data would be ascribed to generally cooled CD effects. And our results could provide a reliable baseline to study exotic phenomena involving partonic degrees of freedom. So now we are also preparing the spin-dependent structure function for the helium-3 calculated with the same approach. And in the future, we want to include off-shell correction, and we also want to do the calculation for heavier nuclei. Thank you for attention.
Any questions for Filippo?
Okay. A quick question. So, you talked about, I missed this. So this EMC effect is on the level of parton distribution function, if I understand correctly. So it has both the information on the parton degree of freedom and also on the nuclear degree of freedom. So how did you combine this information together? Because your let's say nucleus wave function is calculated, if I understand correctly, from the techniques in low energy nuclear physics. So it's fully non-relativistic but the parton distribution function is a relativistic notion. So how do you combine these two parts together in your formalism?
The partonic.
Partonic degrees of freedom. For example, the EMC effect, I think, is this can be manifested from the parton distribution function of the nucleus.
In this calculation, we have only nucleonic degrees of freedoms, so only the nuclear one. When we use the free nucleon structure function, so we don't modify the distribution of the partons inside the.
Oh, you don't have quarks. So basically, your EMC effect is represented as a function of this the longitudinal momentum fraction of the nucleon inside the nucleus, not of the quark.
Yeah.
Okay. I see.
Thank you.
I guess this is related to actually the previous question. That to me, what's really puzzling about the EMC effect, I mean, the mystery, is that just from dimensional analysis arguments, the nuclear binding energy is MeV. So the modification of the quark wave function inside the nucleon should be of the order of the nuclear binding energy divided by the total mass, by the total energy, which is the nuclear mass. So it should be something like 1%. And that's what you get at large NC. But this spectacularly fails.
Yeah.
For example, this spectacularly fails. Is there sort of an explanation, basic physics explanation as to why this fails?
Maybe short range correlations, we have nucleons that so fast nucleons, and that we I think of that. I don't know.
But why doesn't this bring the nuclear binding energy to a high value? If you have short range correlations, they're high momentum, and then the nuclear binding energy should be of the order of the nuclear mass, which again, from large NC, that's exactly what happens.
Thanks. A very super quick question. I'm still lost. Is there a simple way of explaining what physics, what dynamics causes the CMC? I don't understand it. You have a simple picture
of the
what's the dynamics? What's causing EMC? Short range correlations, or what is it?
Maybe, yeah, short range correlations. Also, the fact that the nucleons move inside the
motion of nucleons inside the nucleus.
And we have to treat. We have the effect of the boost within the reference frame of the nucleons, and the reference frame where of the cluster where the nucleons move.
Just an answer or a comment. I mean, this is a 30, 40 years old problem. You know, we still don't have really a solution. And there are two schools. There's the school that wants to do everything with correlations. And then you have the school that wants to modify the system with mean field in the medium, right? So you could try to do it that way. But it's a very interesting problem. We haven't solved it yet. Some people argue, there are Nature papers that everything is explained with correlations, and others that, you know, have also models that will tell you the truth is it's some linear combination between correlations and mean field effects. And the, you know, old ideas where nucleon is swollen in the nucleus and you take a vector minus scalar potential and so on. What I want to ask, that's just a general comment. We don't want to put you on the spot, but I want to discuss your calculation. So that's the conclusion that I'm interested in, the bullet number 3. So you try to the best of your ability to do a nuclear calculations, and where the quark, if you will, enter is just through the structure functions.
Yeah.
Right? And you cannot reproduce.
No,
the
no.
effect is very small. And,
But we
and so-
want to include also
Yeah.
correction.
And the argument that he gave about the binding energy may have some validity in the terms that that's what you seek.
Yeah, yeah.
If you take nucleonic and that your binding calculation, I know from this group that you get the
Yeah,
helium.
we need
4.
something else to explain the effect.
That's right. So to explain the effect, but this is actually quite important because there are so many claims in the literature right now about, oh, everything is explained with correlation. You are telling me if you do the proper approach in nuclear physics, however, you take the free structure functions of the proton neutrons that were measured recently, right? You can't explain it. Thank you.
Thank you.
It's just more a naive comment on what you said. I mean, the understanding of these papers that talk about correlations being important to explain the EMC effect is the one you find already in the deuteron. They use that. They say that essentially comes from the overlap. And then at short range, you have in your nuclei, let us say, the same kind of overlap. But this is, of course, is not contained here. This kind of effect. It is just from the waveform. You do not change the nucleon parton distribution. Yeah.
Okay, you just had a quick comment or question?
Yeah. I don't remember. GB.
Okay, let's thank all the speakers this afternoon. Everybody have a good lunch. So, Jay, you want to make any announcements or?